Okay. Okay. I hope you can see my screen. Okay. Okay, I have started with a poll so that it's a confirmation. You are able to see all of you are able to see my screen. Okay. All right. So most of you are saying yes. So therefore, yes. Let us move ahead. Is there any doubt in previous class? Whatever we have covered? If you have any doubt, you can either raise your hand or you can put it in the chat. Yes. Okay. It seems there is no doubt. Okay. All right. So next we are going to see a specific case of beams. In the last class we have seen beams, right? Just let me go back. Yes. So the application of beams, you have seen the different types of beams: cantilever, simply supported, and overhanging, continuous beam, etc. etc. That we have seen, correct? What exactly this? What exactly this? So I already told you what are the different types of beams. Cantilever means it is supported at one end, fixed at one end, fixed at one end. So loaded at the other end, loaded at the other end. That is known as cantilever. Then there is simply supported. Both end of the beam is supported. Okay. Then overhanging. So the beam is supported with two supports, but not at the end, but in between. So there will be a overhang. There will be a overhang. Similarly, continuous beam, that is beam is supported at multiple points, more than 2 points. So then it is known as continuous supported beam. Then another type is fixed ended. The beam is fixed, both end of the beam is fixed. Then of course another case is cantilever, simply supported. So we have seen this, correct? All right. All right, let us come back. So we are going to see a particular case. We are going to see a particular case, that is cantilever. Okay. So what exactly cantilever? Just a few minutes before we have seen a thin beam of finite area of cross section fixed at one end and loaded at the other end. So here you can see. Okay. So beam is fixed. Beam is fixed at one end. This end beam is fixed. Correct. The other end you can see at this end the beam is loaded. Okay, so fixed end and loaded end, you can see that. So such type of lot of structure you can see in different application. Okay, so whenever you load the cantilever beam, cantilever beam, it undergoes depression. You can see here. Whenever you load that, you can see it is not straight as the neutral axis. Okay, EF, let us say neutral axis. You see that cantilever bends. You can see the dotted lines. Okay, there will be a depression. There will be a depression. All right. Okay. So you can see the diving plank in the swimming pool. That is also example for cantilever diving plank. Okay. Then the roof structure you can see here. This is again a cantilever. Here you can see the cantilever. You might have seen the bus stand or bus waiting shed. A single pillar. Okay. For that a roof is attached. This is again a cantilever structure. This involves a cantilever structure. Single pillar or multiple pillar, but a hanging structure. Hanging structure. That's again with the support of cantilever only it is constructed. In the same way you can see the signal light post. You can see that uh, it is attached to a pillar. It's pillar. Okay. So a light is again this is a cantilever. You can see this end is fixed. This end is fixed. This is a loaded end. What is a load? Load is nothing but the signal light is a load. Signal light is a load for the cantilever. So similarly, you can see this such type of building structures. Building structures. You can also see this is of course, yeah, this is another example, very good example. So this is actually a railway electrification, the railway electric line. So this is again a cantilever. This is again a cantilever. Okay. So this is a fixed end. This end is fixed. The other end is loaded. Again, you can see here multiple cantilever actually. You can see one more set of cantilever here. Okay. All right. This is what the some of the example for cantilevers. Okay. All right. Now, what is our next aim is before going to next, any doubt at this point? Okay, no doubt. The cantilever is clear, right? Okay. All right. So next, what we are going to do is, so just now we have seen whenever cantilever is loaded, whenever cantilever is loaded, it undergoes depression. You just now we have seen the cantilever undergoes depression. So has nothing but this dotted line. Okay, that dotted line is the depression line. Okay, so this is how depression takes place. So we want to get an expression for this, the amount of depression, the amount of depression with load, how much it undergoes depression we want to understand. So for that we are going to consider a single cantilever. Okay, all right. Let us consider a cantilever of length L, fixed at one end, whereas other end is loaded. Okay, so right. So here, this AB, line AB, this is a cantilever. Okay, so which is having length L, which is having a length L. Okay, so the end B is fixed. Let us consider the end B, end A of the cantilever is fixed. This end is fixed. Okay, the other end B, this is the loading end. This end is loaded. So by an amount W. Whenever it is loaded, what happens? The depression of the cantilever takes place. So like this, cantilever will bend. Okay, cantilever will bend. So up to B dash, depending on what is the load you have added. So some assumptions we have to make at this point. What is that? Yes, Rahul, once more. Can I know which one I have to explain once more? Rahul, you can unmute actually, or you can put it in the chat. Yes, Rahul, which part you need explanation? Previous slide. Okay. Okay, students, I will go to previous slide once again. Because, all right. So, what exactly this? All right. So, what? First, you have to understand what is cantilever. You have seen the last class beams. What are beams? Beams are a structural material which is having length is larger compared to its cross section or thickness. Okay, cross section. So such structure is known as beam. There are different types of beam. Few minutes before we have seen what are the different types of beam. In the last class also we have seen. There is cantilever, continuous beam, okay, overhanging beam, and okay. So different types of beam. So what exactly cantilever? Cantilever is nothing but a beam in which one end is fixed. One end of the beam is fixed. Other end of the beam is loaded. This is a loading end. Okay. One end of the beam is fixed, other end of the beam is loaded. Such type of beam is known as cantilever. A thin beam of finite area of cross section fixed at one end and loaded at the other end. That is known as cantilever. That is the definition of cantilever. Okay. So whenever cantilever is loaded, what happens? The loaded under end undergoes depression. You can see a dotted line. You can see a dotted line. So that is depression. That is depression. Okay. So that depends on what is the load. Amount of depression depends on amount of load you have add and what is the Young's modulus of the beam cantilever. All right. So different places where you can see the cantilever. So this is of course in the swimming pool, whatever diving plank, that is nothing but a cantilever. Example for cantilever, one end is fixed, other end is loaded. Then in the roof you can see this type of structures, they are nothing but cantilever. One end is fixed, okay, other end is free and loaded. Similarly in the bus stop or waiting shed, you can see this type of structure, a single pillar for which the roof is attached. There is no other support. So that means this end is fixed. This end is fixed and this is other end which is loaded. This is possible using the cantilever. You can see here at the bottom. Then the figure may not be clear, but you have seen this type of structure. So that is similar to this structure. So which is connected with cantilevers. Similarly, you can see in the signal light, this is a cantilever, this end is fixed, okay, this is the loading end. So like this structure, again here you can see a cantilever, okay, one end is fixed and other end is loaded. So this is again one more example for the electric post of the railway electric line. So again this connecting part, this involves cantilever. Again here one more cantilever is here. So you can see a multiple cantilevers. Okay. Is it okay, Rahul? Okay. Next, our task is to find out. We understood whenever the cantilever is loaded, it undergoes depression. How much depression it undergoes, that we want to understand. To understand this, let us consider a cantilever, a cantilever which is fixed at one end. Let us say end A is fixed. Okay. Further, whatever line I have drawn here, AB, let us say AB is the neutral axis. You know what is neutral axis in the beam. The line or filament which does not undergo any compression or extension is known as neutral axis. Okay. So AB is a neutral axis. Now, whenever end B is loaded, so with the W, then B undergoes depression to B dash. So this is the point of depression. So you can see a curved line. This is how cantilever bends. So AB get deflected to AB dash. AB get deflected to AB dash. Okay. All right. So now another assumption we have to make is, so beam does not uh, get bent, that is cantilever is not going to bend because of the weight of the beam or mass of the beam. Because of mass of the beam, it is not going to bend. So now what we will do is, let us consider a section in the beam. Okay, consider a section P. at a distance x. Let us say at this point, okay, let us say that is P. So that is from fixed end. What is the distance? Distance is x. Distance is x. So now, what we assume is the distance PB, and the distance PB dash. So that same cantilever is bent. Okay, the same cantilever is bent. So therefore, that's the same point. What we are going to assume is the distance PB, that is, which is at distance, this distance. PB is nothing but this distance. Okay, PB and this distance PB dash, they are approximately same. I used equality symbol, so it should be approximately same, So therefore, PB is equal to PB dash, that's equal to, what is that? L minus X. Okay, all right. So, what is the bending moment produced at P? Bending moment produced, that is because of the weight W into, so you are looking at from the point P, what is the amount of bending moment. So therefore, length is important. What is the length? L minus X. W into L minus X. Then, if it is undergoes bending, then there will be a restoring force acting on it. That is given by Young's modulus into, this already we have seen, okay, in the bending of beam. So Young's modulus into geometrical moment, that is Ig, divided by radius of curvature. So we have to understand restoring force and bending moment are acting in opposite direction. So therefore, they will come to an equilibrium. Okay. Then the two forces are equal. So therefore, you can equate. So bending moment is equal to restoring force. So that is W into L minus X. W into L minus X. Okay. Bending moment is this much. This is a restoring force. So therefore, W into L minus X, that's equal to Y into Ig by R. So all the terminologies are known, correct? Okay. So let us go further. So already we have considered a a point P, correct? This is a point P that is deflected now at this point. Okay. In the same way, let us consider one more section very near to P. Let us consider section Q. So let us assume that P and Q are very close to each other. Then radius of curvature of point P and point Q are one and the same. Both sections are one and the same. So radius of curvature, let us say R. Even OQ and OP, that's equal to R. Okay. Then that is R is a radius of curvature, and d theta is the angle between radii of curvatures of PQ, P and Q. So it's a radii angle between radii of curvature of P and Q. Correct na? This is P, this is Q. So this is a angle between them. Right? If dx is a distance between P and Q, okay, let us assume the distance between P and Q, this distance, okay, my line is got bent, no problem. Let us say dx is the distance between P and Q. Alright. Then dx can be written as, because you know P and Q are very close, very close. So radius of curvature are one and the same. So then you can write dx is equal to r into d theta. Correct? So you can get an expression for radius of curvature, that is on rewriting r is equal to dx by d theta. Dx by d theta. Okay? Right? So at this moment, let us take the previous expression. What was that? The previous expression we had, uh, just to go back, what is that? W into L minus X is equal to Y into Ig by R. So radius of curvature was there. So same thing can be substituted. You got an expression for radius of curvature. So therefore substitute that expression R. So therefore you will get W into L minus X is equal to Y, capital Y. Please carefully note this is a capital Y. Okay, capital Y, Ig, geometrical moment. So divided by R, that is dx by d theta. So 1 by R, it can be substituted reciprocal of this, that is d theta by dx. So therefore angle between two radii of curvature, so of P and Q, expression can be written as from this d theta is equal to W into L minus X divided by taking this okay, Y and Ig to other side. So alright, Y divided by Y into Ig dx to other side. So therefore into dx. Call that as equation 2. Now what we will do is, let us draw tangents at point P and Q. What is that? So you can see that tangents. So PC is the tangent drawn. PC is the tangent. Okay. PC is the tangent drawn. Right. The same way. Okay. PC is the tangent. Then another tangent. QD. Right. Two tangents are drawn. Two tangents are drawn. PC and QD. Then let d theta. Let d theta be the angle between those two tangents. Okay. Again d theta is a angle between two tangents. Now you draw perpendicular line from Q to the PC line. Okay, PC line. Let CD be the depression. So that means small amount of depression by so CD, let us call it as dy. Let's call it as dy between point P and Q. Small depression. So a segment we have considered. So therefore you can write d theta is equal to dy divided by L minus x. Why it is L minus x? So whether it is PB or PC or PB dash. Okay. So we assumed approximately they are equal. So therefore d theta is equal to dy by L minus x. Call that as expression 3. So on rewriting, so what was the previous expression? So you have two d theta expression. What I will do is I'll just take this expression to next slide so that you can see next slide also. Okay, second expression. Okay, here it is. Just a confusion. Okay. Here I pasted. Okay. All right. Just paste it somewhere. The other slide. Okay. Expression 3. Expression 2. Actually, where exactly I pasted? I missed somewhere. Okay, no problem. Just to show. By mistake I pasted in the slide. I'll remove that. Okay. All right. So okay, you got okay. You came up to this point. Okay. Okay, Mayur has asked L minus X is it a depression? No, no, it's not. L minus S is not a depression. That is the initial assumption we made. A section P and PB dash length of PB dash. PB and PB dash are equal. That's what exactly we assumed. So if PB dash and PB are equal, even PC also equal, na? So therefore PC is nothing but L minus X. So therefore you got d theta is equal because this angle is, that is what is that? PC and PD angle is d theta, d theta. So therefore d theta is equal to dy by L minus X. Clear? Okay. Is my voice is clear? Audible? Okay. All right. Okay. Okay. Next. Let us go to the next slide. So you have two expression for d theta, that is d theta is equal to w into L minus x, that is expression second and expression third. So therefore you can equate that. So therefore dy by L minus x is equal to w into L minus x divided by y into ig dx. So here important point I wanted to make a note, you have to make a note as that is, what is that? This capital Y, okay, this is small y. Don't get confused. Capital Y is Young's modulus. This is Young's modulus. Okay, this is Young's modulus. Okay, this is Young's modulus. Whereas this small y is depression, bending. Okay, so therefore that you have to keep it in mind. Alright, so don't get confused. Alright, so let us rewrite that. Let us rewrite that. Dy is equal to, our aim is to find out expression for depression. Okay, so dy is equal to, what happens on rewriting this L minus x, L minus x goes to other side. So this L minus x goes here. So therefore it becomes dy is equal to w into L minus x whole square divided by y into ig dx. So this is a small depression between 2 points. Okay, that is tangent drawn between for P and Q. Suppose if you want to depression for the whole cantilever, that is amount up to PB dash, you have to integrate this. This is the small depression between 2 points P and Q. Similarly, you have to draw number of tangents. You have to consider a n number of points. Okay, you have to draw the tangents. So you will get a dy. So integrate that. So therefore, integrating with respect to y. So y is equal to w divided by y into ig. So this is okay. So which is a constant. So therefore, you kept outside. Okay. So this portion is constant. This is a constant. So you kept it outside. So integrating. Okay. L minus x square, L minus x whole square dx. Right. So on integrating, what do you get? L. Okay, constant, keep it as such. Inside, first expand this. While expanding, what do you get? L square plus x square minus 2lx, L minus x whole square while expanding. Now you integrate that. What do you get? The constant remains as such. So L square x plus x square becomes x cube by 3 minus 2lx. On integration, x square by 2. 2 will get cancelled. So you are left with Lx square plus c, which is a constant of integration. C is a constant of integration. So how to get the value of c? Value of c can be obtained by using boundary condition. Okay. All right. That's the expression for whatever we got. So let us try to get put the boundary condition. So let us take the first boundary condition. So at the fixed end of the cantilever, what is the depression? at this point, what is the depression? That is 0, correct? That is x is equal to 0. What I am talking is when the x is equal to 0, x is equal to 0, y is also equal to 0, no depression. Okay, so if you substitute this boundary condition, what is that? X equal to 0, y is equal to 0. What do you get? What happens? So you will get x is equal to L, correct? Right? So therefore depression produced in the cantilever, substitute the condition. So what you get is, so y is equal to W by y into Ig L square x plus x cube plus by 3 minus Lx square. So that means constant c is eliminated because c is equal to 0. C is equal to 0. Alright. Next. Uh, so now let us say cantilever length is L, okay, maximum. So x value substitute it as L, So then what happens is the equation becomes L square into L. So therefore L cube, x cube, that is L cube, minus L into x square, that is L cube. So therefore you will get depression y is equal to W into L cube divided by 3yig. Okay, so important thing is, again I'll bring your notices. This is small y, this is depression, this is capital Y, this is Young's modulus. Okay, clear? All. So before that, okay, let us go back. So now this is a expression for depression. This is an expression for depression. Okay, this is a expression for general expression for depression. Now, whenever you consider beam, there are two types of beam is possible. One is geometrical cross section is equal to rectangular, another one is circular. Let us consider a beam with geometrical cross section, rectangular cross section. Okay, rectangular geometrical moment. What is the geometrical moment for rectangular cross section? BD cube by 12, that we have seen in last class. Okay, so let us use that in equation, the previous expression. So Ig is substituted. So if there is a confusion, I will bring the other equation to, okay, previous expression. Let us bring that. Control C. Okay, this expression, general expression. Okay, this is a expression. When you substitute, okay, and you substitute for Ig. Okay, let us substitute for Ig. So y is equal to W into L cube as such. So now 3y, that is okay. You are substituting for Ig. What is Ig value? BD cube by 12. BD cube by 12. So BD cube by 12, if you substitute, okay. So what do you get? In the denominator BD cube, that 12 goes to numerator. So therefore WL cube into 12 divided by 3y 4D cube. So 3 and 12. So it goes. So you are left with 4. 4 WL cube divided by BD cube. Okay. Of course, I just bring your notice. This is capital Y. If you are getting confusion, what you can do is you can write this Y as Y naught. Okay. Y naught. This is expression for Young's modulus of the cantilever with cross section, a rectangular cross section. If it is circular, if it is circular cross section, what is the geometrical moment? If it is circular, Ig is equal to 5 into x to the power 4 divided by 4. Where x, what is x? What is x? X is the radius of the beam. Okay, x is the radius of the beam. Again, substituting on this equation, what do you get? Y is equal to WL cube divided by 3y pi x to the power 4 divided by 4. Go to numerator. Y is equal to 4WL cube divided by 3y 5x to the power 4. So this is expression for depression of a cantilever having circular cross section. Is it okay? So this is a general expression for any cross section. Y is equal to WL cube divided by 3yIg is the general expression for depression. So this is for rectangular cross section. This is for circular cross section. Is it okay? So I think it's time. We'll stop here. Already it is time. So I will stop. So I'll take attendance poll. Once attendance poll is over, you can leave the class. Okay. I'll give the attendance poll. Okay, 1 second. Let me. Okay. Okay, new poll I will launch. Okay, I have opened the attendance poll. You can put your attendance and you can leave the meeting. Thank you for joining. So let us see tomorrow. So let me see. I am going to put the link for tomorrow's class, but tomorrow there is a meeting. If it is possible only, I will take the class. But anyway, I will create the link and send you. Register yourself. If there is a class tomorrow, we are going to solve the problem. So be ready with calculators. Okay. All right. All right. See you tomorrow. Thank you for joining the class. Put your attendance and you can leave the poll. If you want to ask anything, you can ask, no problem. You can unmute yourself and you can ask. So I will stop sharing.